Okay, for this hypothesis test, we're going to do a test of proportions. So it's slightly different from the other two tests, but very similar in structure as well, right? So let's look at the question that we have. The following is based on information from The Wolf in the Southwest, Making of an Endangered Species, by David E. Brown from the University of Arizona Press. So before 1918, the proportion of female wolves in the general population of all southwestern wolves was about 50%. However, after 1918, southwestern cattle ranchers began a widespread effort to destroy wolves. In a recent sample of 34 wolves, there were only 10 females. One theory is that male wolves tend to return sooner than females to their old territories where their predecessors were exterminated. Do these data indicate that the population proportion of female wolves is now different than 50% in the region? We want to use an alpha equals 0.01% alpha value. Okay, so our significance level is very small here. Okay, meaning that my sample needs to be very, 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 very different than what I'm assuming it to be in order for me to reject the null hypothesis. Okay, so this is giving me a lot of wiggle room, probably because I have a small sample size, right? Even though we're doing a proportions, 34 wolves, if you think about the population of any animal, is generally very large, right? So if they were only able to contact 34 and find 10 females, that's not a lot, right? So I need to make sure that my sample is very, very, very different from my population mean in order for me to say I don't think that this is true anymore. Okay, so let's start this off. Okay, so sometimes we have to read these things a couple times. There's a lot of information given here. There's some information that's not very useful and some is very useful, right? Like 1980, 18, it gives an idea of when these kind of research was happening and when a change in the attitude towards wolves kind of happened, but it's not really giving me any information towards me solving this problem, right? So I want to make sure I have the important pieces. The important pieces of information is my assumed population mean. I'm assuming that half of the wolves are female and half of the wolves are male, right? That kind of makes sense. I'm also given that my sample size was 34, and out of those 34, I had 10 successes, right? So remember, a proportion is when we have sort of a yes or no kind of thing, right? So I collected a sample, I had 10 yeses in my sample. My yeses are female, right? If I had a wolf that was a female, that counts as a yes. So I have a proportion of females. That's how I know that this is a test for proportion and not a test for means. It's not saying I had an average value of this thing from my sample. It's saying that I had 34 wolves, 10 of them were female. That will give me a proportion. In fact, that's the first thing I can calculate. What is my proportion? My sample proportion, p hat, is x over n. My yeses over my sample size. I had 10 yeses out of 34 sampled. I have a p hat value, a sample proportion of about 29.41%, right? Or 0.2941 is how I would use that, right? So that's how we know whether or not we're using proportions or means, is because I'm pretty much having a yes or no question. I have a certain number of successes out of a total number of data objects selected, right? So to get this test started, again, the first thing I need to do is figure out what my null and alternative hypothesis is. So I'm assuming that half of the wolves are female and the other half are male. Okay, I'm trying to test whether or not there's a difference, right? So my null hypothesis is that the actual proportion, just p here, not the p-value, is very different, just p, that the true population proportion is 50%. Okay, and basically what I'm testing is this value that I have way different from 50%, basically outside of my cutoff range or not. Okay, that's the big idea, right? So I got a sample mean of 29.41. Is 29% super far from 50%? Far enough for me to say that my null hypothesis, that it's 50-50, is correct or not, right? That's what I'm testing. So my null hypothesis is that it's 50%. My alternative is not that it's less. My alternative is that it's different. So my alternative hypothesis is that I have something different than 50%. So that gives me a non-equals. Okay, a non-equals because I'm looking for a different than 50%. I'm not doing less than, even though my sample is saying that it's pretty much less than what I'm assuming is true, right? I'm doing a difference test, right? Is it different than what I assume it is, right? So what that means is that this is going to tell me what kind of test I'm running. Okay. Remember, the alternative hypothesis tells me whether I'm doing a left tail test, a right tail test, or a two-tailed test. Right. So remember, I follow the sign on the alternative. So not equals means two-tailed test. So I'm going to do a two-tailed test for proportions. Okay. Two-tailed test for proportions. Right. So next thing I need to do is I need to verify the conditions for my central limit theorem. Because again, if I don't have the conditions to use the central limit theorem, then I cannot use the central limit theorem. So I need to check randomness. I need to check that my sample results are independent of each other and that my distribution is approximately normal, so I can calculate things with normal CDF and inverse norm and z-scores and all those things that have to do with the normal distribution. Okay, so my first condition is randomness. So this was conducted by some researchers, and it stated that my sample was randomly collected, right? Where is that stated in here? It says in a recent sample of 34 wolves, 1/3 that male wolves tend to be returned to certain other territories. So I guess it doesn't say that it was random, but I guess we can so if it's not stated that it's random, then we can assume randomness, right? So let's make a check here. So it's assumed that the sample was randomly collected since conducted. Actually, I don't even have to say that it's assumed, right? My chances of running into wolves is pretty random. I can't select which wolves I'm going to run into, right? So I guess we can say that the sampling of wild wolves will be random. Okay. So again, it's not very cookie cutter. We have to sort of explain why it's going to be random. Either we're told it was randomly collected. Maybe this was done by researchers. So their job is to sample things and collect data, so we know that they should be doing a pretty good job. Or if we're collecting things out of the wild, the selection process is kind of out of our hands at that point, right? So we can assume that this is pretty much random. Okay. Next thing I need is independence. Okay, 34 wolves out of all of the wolves in the Southwest. Hopefully this is a pretty small population, right? So I hope that there's more than 340 wolves. You really couldn't tell unless you tagged all of the wolves that you come across, and then every time you come across a wolf, hopefully they're not tagged, right? But we're going to assume that they're all independent of each other and that we didn't sample the entire population, that there's not only 34 wild wolves in the Southwest. Okay. The next thing that I need is normality. So when we're using proportions, we basically need to make sure that we have more than 5 expected successes and more than 5 expected failures. That's the only thing we need to kind of ensure that we have a normal distribution. Okay, so when we do this, we're looking at n times my assumed p-value. I'm not going to do p hat right now, what actually happened, but what I would expect to happen if this is true. So whenever possible, I want to use this value for p and not my sample p hat, because this is coming from a collection of things, and this is based on my assumption, right? So I'm going to always use this value whenever I can because it's my assumed true value. Right? So for normality, the expected number of successes is my sample size times my what I'm assuming to be true proportion. So 34 times 50%, which is 17. That's greater than 5. I would expect out of this 34 wolves that I gathered that 17 of them were female, and I would expect that 17 were male, right? That would be my expected number of failures. So that's the next thing that we look at. Right, so if my expected number of successes is half, 17, well, the other half is my expected number of failures. So I would expect 17 females, 17 males. Both of those are more than 5. So my distribution of proportions is approximately normal at this point. Okay. The next thing that I need to do is I need to look at what my significance level is, right? What am I testing this at? In this case, it's at the 1% value. Right, so we will be testing at the alpha equals 1% level of significance. Okay, so the next thing that I want to do is I want to look at my graph, and again, I don't just start with the graph. I got to find some values. I got to find my test statistic that's coming from p hat, and I need to find out what my cutoff level is in terms of z-scores. So I'm going to turn this into a z-score, and I'm going to look at the z-score for my cutoff level, my level of significance, and I'm going to see, is this in the rejection region or is it not in the rejection region, right? So is this past the critical value or not past the critical value? Okay, so for my critical value, let's put this back down. Okay, I need the z-score for my p hat value. So p hat was 0.2941, so I need the z-score for 0.294 for my distribution of proportions with this with this standard deviation, right? So the standard deviation for proportions is the square root of p times q over n, and I have to find the difference between my sample proportion and what I'm assuming to be the true proportion. So 0.294 is my p hat, minus 0.5, which is my assumed p-value, true proportion, I should say, divided by, and I'm using p and q here, where I have p is 50%, so q is also 50%, and my sample size was 34. So when I do all this, my test statistic turns into negative 2.4012. Now, just a quick heads up, this is a two-tailed test, okay? Two-tailed test means that I have a z-score on the negative side and a z-score on the positive side when I look at my distribution. Okay, so this is going to be the z-score for the left side, and I'm going to need a z-score for my right side, which would just be the same number but the opposite value, so positive. Okay, now I need a z-score for my alpha level. Remember, this is a two-tailed test, so this 1% needs to be split in half. So my critical value on my left will be 0.5%, and my critical value on the right will also be 0.5%, right? Because together, those two critical values need to be an area of 1% of my total graph. So what we're going to do is we're going to take my alpha level and cut it in half. Very similar to what we do for confidence intervals, although I'm not necessarily creating a confidence interval. I kind of am creating a confidence interval, right? So a lot of the work is somewhat similar, right? And the graph will look somewhat similar as well. So I take my z-score for my critical value, my cutoff region, right, my rejection region, and I cut it in half since I'm going to split it between the left side and the right side. So I need the z-score for 0.005, right, an extra 0 in there. So inverse norm of, again, this would just be 0.005, and then your standard normal distribution. So this is my critical value on the left side. For the right side, it'll be the same value except for positive. Okay. So again, remember, we're splitting this into two pieces, right? Let's take a quick look at our z-score. I'm sorry, our p-value. And then from there, we can look at our graph, right? So generally, we would look at the graph first, but I like to put the test value, the critical value, and the p-value all on the graph at the same time. Okay, so my p-value is the probability that the absolute value of all possible z-scores are larger than the test value that I have. So remember, absolute value means everything will end up being positive, so it wouldn't make sense to make this positive. Although when we look at our graph, we look at the positive and the negative values, and here I just have my two negative values. I don't have to write both of them, I just need one, right? But remember, absolute value means the positive portion, okay? So I'm splitting this in two, right? Because if I have absolute value of 1 is 1, absolute value of -1 is also 1. So when I'm taking the absolute value of z-scores, all of the positive values are taken into consideration, and all of the negative values are also taken into consideration because the absolute value of the negatives are positive, right? So all of this assuming that my null hypothesis is true. So I'm really going to just look at one side. Here I did the left side because that's the z value, the z-score that I found, right? Just for my proportion, it happens to be on the left. It's negative. So I find the normal distribution, the normal CDF, from -infinity up to my test statistic, and that's only one tail of the test, so I have to double that so I can take into consideration the right tail, and that's how I get the 0.0163, right? So if we look at the graph, we'll see that we have a left tail and a right tail in consideration, and everything there is basically split in half, but we just look at 1/2 and double everything, and that's how we get all of our values. Okay, so again, we'll start off with our critical region. Instead of alpha as 1%, I'm putting it at 0.5%, but I'm splitting it between the left and the right tails. So when I look for my z-scores, I'm doing a z-score for the alpha equals 0, for the 0.5%, right, 0.005. And then I'm doing the left side and the right side, so altogether, this alpha plus this alpha is 1%, or 0.01. So I have the z-score for one side and the z-score for the other side. Altogether, that gives me the full 1%. So when we compare this to what we actually get, okay, then you can see that my z-score for my x value, right, for my sample proportion, this should be p hat, not x bar, okay? But when I get this value, it is less than my cutoff on both sides, right? I am outside of my cutoff. I am in this case in the green, okay? I can shift these a little bit around so we can see that we're on the outside, right? If we try to look at what our p-value is, it looks something like this, okay? The p-value is the probability of the absolute value of z of, again, p hat, apologies, right? Assuming that my null hypothesis is true, is 0.16, basically 3, right? We cut it off at 4. So this is more than my cutoff value. It's larger than my alpha. My alpha is 1%, and I'm looking at 1.63%. So I'm close enough to my mean that I am not going to reject. I'm not in the rejection region, right? Mean of 0, standard deviation 1, and these are my x of p hat values, right? I should have changed those. Okay, so quick correction. Now it says z of p hat, c fat, whatever you want to call it, it's fine. Right, so my z of p hat, just so that we had one graph that kind of made complete sense, right? So let's go back to the work that we had and talk about our conclusion. Okay, so for our conclusion, again, we compare our p-value with our alpha value, right? My p-value is larger than my alpha value, so we fail to reject H0. Okay, so again, my test value is closer to my center than my cutoff value, right? My cutoff value is farther away from 0 than my test value, because these are z-scores, right? 0 is at the center, and we just looked at the graph also, so it makes sense, right? What does this mean in context? Okay, so we conclude to fail to reject H0, meaning that I am not going to reject this, but that doesn't mean I'm accepting it. Do not write you're accepting this, right? It just means I don't have enough evidence to say that this is false. Maybe it is false. I just don't have enough evidence to show that yet. Okay? So there is not enough evidence to suggest that my population proportion of female southwestern wolves is not different than 50%. I can't say that it's not this thing. It could be that it's true, but I can't say that yet. I don't have enough evidence to prove that that is true. Okay. So the next thing I want to talk about is my possible error, which is maybe I'm wrong. Maybe it is different from this thing, right? I just don't have enough evidence to show that. So the possible error that I made is that it actually is different. Okay. And that's what we call a type 2 error, right? So it's possible that we concluded to fail to reject H0, the null hypothesis, when the null hypothesis is actually false. So what does that mean in context? Well, we conclude that the population proportion of female southwestern wolves is not different from 50% when it actually is.